Chapter 35, Hess Law. If you want to travel from Ch35 to Lam Tin via MTR, you may choose either one of the following routes. Route 1. Take the red-green lines by traveling through 13 stations. Okay? Or you may take another route, Route 2. Take the red, blue, purple, green line by traveling through 8 stations. Can you see that? There are 2 routes, but with the same starting point and the same final point, Route 1, and it is Route 2. No matter which route you take, when you finish your trip, you will be charged the same fare, okay? A similar concept is found when we study chemical reactions. Underline the next sentence. If the initial and final states of a reaction are the same, no matter which route a reaction takes and how many steps are involved in the route taken, the enthalpy change accompanying the reaction will always be the same, like the fare, okay? You will be charged the same fare. Now underline, if the initial, that means your starting point, and the final states, that means the products of a reaction are the same, no matter which route a reaction takes, and how many steps are involved, the enthalpy change accompanying the reaction will always be the same. Okay, here are the main points. Please bear in mind. Actually, it is Hess law. Now let's try to think about why is the enthalpy change of a reaction independent of the reaction route? Independence on the reaction route. Now, first of all, do you remember what is delta H? Delta H is equal to the enthalpy of product minus the enthalpies of reactant. Do you remember? So, by using this equation, we can explain. That is because enthalpy change of a reaction depends only on the difference in enthalpies between reactants and products. Therefore, the enthalpy change of a reaction is independent of the reaction route. Next, how do chemists use the above concept to determine enthalpy changes that cannot be found directly by experiment? Chemists can apply Hess law. I'm going to talk about Hess law to calculate the enthalpy changes that cannot be found directly by experiment. Please copy down this answer and highlight. Chemists can apply Hess law to calculate the enthalpy changes that cannot be found directly by experiment. Now please turn back to chapter 34, page 23. Let's have a revision. It's about the determinations of enthalpy change of formation. Direct determination of enthalpy changes of formation by simple colorimetric methods is difficult in most cases. It is because some formation reactions are highly exothermic and cannot be safely carried out. And another one, side reactions may lead to the formations of side products. I have already discussed this with you. Now let's look at this example. It's about the standard enthalpy change of formations of calcium carbonate. First of all, look what is the definitions of the standard enthalpy change of formations of calcium carbonate. It is the enthalpy change when 1 mole of calcium carbonate, 1, is formed from its constituent elements. Its constituent elements are calcium metal, carbon graphite, and oxygen. Bear in mind, we need to keep 1 according to the definition. Therefore, balancing this equation, you need to put 3/2 before O2. If we carry out direct experiment, okay, lots of side reactions occurs. Like carbon actually like to oxidize to form carbon dioxide. Instead of forming calcium carbonate, carbon dioxide is formed. On the other hand, calcium likes to react with oxygen to form calcium oxide instead of calcium carbonate. These are the side reactions. These two are the side products. Okay? Therefore, direct determination of the enthalpy changes of formation is difficult. Here I would like to give you another example. It's about the enthalpy change of formation of ethane. For Form 4 students, you haven't learned how to name. When we have 2 carbon, if there are 2 carbons, then it will start with ETH. Okay? In the molecule, all are singly bonded. And it ends up the name with ANE because it belongs to this family, alkane. Now let's talk about the definition first. Can you please write down the definition? Standard enthalpy change of formation of ethane. Please pause the video, write down the definition, and then check the answer. Is the enthalpy change remember, start the definition by repeating is the enthalpy change when 1 mole, this is very important, okay? 1 mole of ethane is formed from its constituent elements. Its elements are carbon graphite and hydrogen gas. Okay? Elements, okay, you must mention under their stable physical state. That means carbon, we are referring to graphite, not diamond, under standard conditions, because we have the term standard enthalpy, so you need to end up your definition by telling me under standard conditions. Now let's look at the equation for the enthalpy change of formations of ethane. Formations of ethane, that means ethane is the product formed from its element. Its elements are carbon graphite and hydrogen gas. In balancing this equation, keep this coefficient 1 and then put 3 in front of hydrogen. This is again, okay, it is impossible to determine its enthalpy change directly because there are a lot of side reaction which will form side product. What are they? Now imagine if you try to react graphite with hydrogen, there are lots of products like methane, ethane, propane, butane, etc. A lot. Maybe ethene, okay, or propene, so lots of side products are produced. In other words, it is not possible to determine the standard enthalpy change of formation of ethane directly. So let's go through this page. Importance of Hess law. As mentioned in the previous chapter, it is sometimes difficult to measure the enthalpy change of a reaction directly by experiment. An indirect method which is based on Hess law has to be used. What does Hess law state? Based on the experimental measurements of enthalpy changes, in 1840, a Swiss-born Russian chemist, Germany Henry Hess, proposed Hess law. Hess law states that the overall enthalpy change of a chemical reaction is the same, regardless of the route by which the reaction takes place, provided that the initial and final states are the same. Now, you may imagine by using this MTR map, okay, the overall charges is the same, okay, regardless of the route by which you take. That means you take this route from Tsim Sha Tsui to Lam Tin, or from Tsim Sha Tsui to Lam Tin. Okay, there are several routes. Regardless of the route by which you take, provided that the initial and final states are the same, provided that the initial station and the final stations are the same. Understand? Okay, try to remember. Now, in other words, the enthalpy change of a reaction depends only on the difference in enthalpy change in enthalpy between the reactants and products. Of course, this sentence is true. Let me write down the definitions again. Do you remember what is enthalpy change? Enthalpy change is the enthalpy of product minus the enthalpy of reactant. Do you remember? In other words, enthalpy change depends only on the difference in enthalpy between the reactants and the products. It does not depend on the route. Please highlight this sentence. It does not belong to the route taken to get from the reactants to the products. Understand? So let's use this as an example again. Here we have route A, carbon elements, hydrogen elements combine to form ethane. The delta H of this route is negative 84.7 kJ per mole. Imagine there is another route, route B. Carbon reacts with hydrogen, first of all, to form C2H2 with the name Ethane. You haven't learned about this term before, okay? With delta H1 equal to 226.7 kJ per mole. Next, Ethane reacts with hydrogen to form ethane with negative 311.4 kJ per mole. Now maybe I would like to use an enthalpy level diagram to illustrate their relationship. Do you remember what is an enthalpy level diagram? First of all, label the y-axis. The y-axis is enthalpy. X-axis is reaction pathway. Sometimes you may miss the x-axis. Actually, x-axis is meaningless. Route A, from this element to the product. with a negative sign, that means pointing downward. So let's start. I'll draw the reactant here. 2 carbon graphite react with 3 hydrogen elements pointing downwards. Ethane with enthalpy lower than the enthalpies of the reactant. Delta HA is equal to negative 84.7 kJ per mole. This is root A. Now, I will highlight this is root A, okay? Now let's talk about root B. Root B. First of all, we have carbon, we have hydrogen to form ethane with a positive sign 226.7. Positive. Positive, that means endothermic. So I must point it upwards. It doesn't matter, not to scale, okay? 2,3H2 with delta H 2, 1 plus 226.7 kJ per mole. This is the first step of root 2. I highlight it in red. And then next, another step. Follow step 1. From ethane, react with hydrogen to form ethane. Okay? That means same ending point. With a positive, with a negative sign, 311.4. Negative 311.4 kilojoule per mole. Again, I highlight this in red. It represents root 2. Now, based on the enthalpy level diagram, can you see that? Okay, the sum. Root 1 first, okay? This is the first root. Root A is negative 84.7 kilojoule per mole. Now let's look at root B. That means the root in red. With the summation of 226.7 plus negative 311.4, which is, use your calculator, 226.7 minus 311.4, which is 226.7 minus 311.4, negative 84.7 kilojoule per mole. Can you see that it is equal to the enthalpy of root A? Okay? So, by using this example, again, let's write down Hess law. What is Hess law? Hess law states that the overall enthalpy change, you may imagine that is the overall charge of a chemical reaction, is the same, will be the same, okay? Delta HA, delta HB are the same. Regardless of the root of the root by which the reaction takes place. Okay, provided that, of course, provided that the initial and the final states are the same. Please try to remember this definition, Hess law. This is what Hess law said. Now turn to the next page. There is a third root starting from the same carbon graphite and hydrogen, end up with the same product, C2H6, but the product in the middle are different. C2H4 reacts with hydrogen. The first step of root C with positive 52.3 kJ per mole. The second step is negative 137.0. Now I would like to draw these two on the same diagram so that you can understand easily. Now remember, this is the first root in green. This is the second root B in red. Now I will draw the third root. The first step, positive 52.3. We should pointing it upwards. Now I will color it later, okay? Upwards. C2H4 gas with delta H equal to positive 52.3. I will color it in red. It is the first step of root C. And then after the first step, we have the second step. From C2H4 react with hydrogen, okay, to form with the same final product, with the same, okay, with negative 137.0 kJ. This is the second step of root C. Now again, I will try to compare the overall enthalpy change of root A. This is the enthalpy change of root A, negative 84.7. And then the overall enthalpy change of root C in red is equal to the summation of 53.3 plus negative 137. Again, take out the calculator, which is negative 84.7 kJ per mole. Can you see that is also equal to the overall enthalpy change of root A? Understand? So use this enthalpy level diagram. You can see that regardless of the route by which the reaction takes, root A, root B, or root C, the overall enthalpy change of a reaction is the same regardless of the route by which the reaction takes place. Of course, provided that with the same initial and final states of the reaction. Understand?